Hello everybody, my name is Ever Barbero and today I want to talk about fracture mechanics. This is video number 3 in a series for fracture mechanics. The first one explains the experimental evidence and the background to understand what's going on. The second one develops the equations to do the design, analysis and design. And once you have seen those two videos, then you can tackle this one, where I'm going to show you two examples using the equations for analysis and second example for design. Okay, so from the previous videos we have learned that if there is a crack, the material fails when the stress intensity exceeds the fracture toughness. So this is a failure criterion, all right, for fracture mechanics. And there might be a crack, or if you're designing, you have to assume that a crack may appear or may be there, all right? And we have discussed all these issues. Now, this stress intensity is called Ki, and is calculated as beta, which we get from charts, and sigma, which is calculated as if the crack is not there. That is mechanics of material formulas. And then A is the crack, that either we know what crack we have, or we assume what crack we might have, what crack we can tolerate. And if we have to assume the crack, then we have a rule to do that, which is this. We take the crack length, that is the smallest crack that the inspection technique can see. So we have to decide how we're going to inspect the part, and then we can choose a size of a crack that we can detect. So armed with this background, we proceed to some practical example. But you understand that if you didn't see the other two videos, it's going to be very difficult, okay? You're going to make mistakes. And so it's better to take the time and watch the other videos so you understand what I'm talking when I do these examples, okay? So first example is an easy example. Calculate the load at failure. So this is an analysis problem because they're asking us for the load that this plate can take when this crack is there, but they're giving us everything. So we don't have to decide anything. We are not designing. We don't decide anything. They say the material has yield strength 950, KIC, this is fracture toughness 80 units, MPa square root of meter. Crack length is 16, so okay, somehow they measure the crack. Dimensions of the plate, H 100, 100, B 100, and thickness is 12. So everything is given, is analysis. Calculate the load P at failure, okay? So either whether we do an analysis or design, if we suspect or we know there is a crack, the analysis and the design, we always have to do yield first. We have to check yield first. All right. So first we're going to calculate the load that it will take to break this specimen, or actually get this specimen into plasticity, widespread plasticity, which we will say failure because it's yielded. And it's an approximate calculation because it's not going to take into account the peculiarities of the crack, all right? So it's like a back of the envelope calculation, but we have to do it, okay? Always we have to do first to see if the part is designed correctly for yield. And then we do fracture. So first of all, we know that the applied load produces a far field stress. This is the stress far from the crack, which is P divided by the area, T times B. T is the thickness, B is the width, so that's the area. That's mechanics of material formula, all right? But to do the yield calculations of P, we have to use the net area because we don't have T times B, because B has a crack that is being cut with a hacksaw, and it's 16 millimeters deep out of 100, so that means 16% of the cross-sectional area is gone. So you cannot use the total area, the nominal area. You have to use the net area, what remains. And what remains is from here to there, all right? So area net is T B minus A, 100 minus 16 times 12, 1008 millimeters squared. So then to calculate the load in an approximate way, I'm going to repeat this because this is not very accurate. the load that it will take to yield this plate is approximately the product of the yield strength multiplied by the area that I have. All right, so it will be like the inverse of this formula, but replacing sigma by S sub y. So if you put sigma S sub y there, multiply by area net, but not this area, and then you get the P. So 950 times 1008, 958 kilonewton. So approximately, if you put 958 kilonewton, this plate will fail due to plasticity, to yield. Okay, now we calculate a fracture, which is what we wanted to do because there is a crack, so this is going to be the important one. So we got the formula, just to remind you. Stress intensity is beta sigma pi a, okay? So first thing we do is get the geometric coefficient beta, which we get from this chart, which you have seen this chart before. So to do that, we need the AB ratio and we need the H over B. H over B is, H is 100, B is 100, so H over B is 1. So we're going to pick this curve. And then the A over B will be the crack divided by this. That's 16 over 100, 0.16. So we know we got to take this curve. And then 0.16, well, is somewhere here. And so we go up like this. And then from here we go this way. And it looks like it is about 1.3. So I pick 1.3. With these charts, you cannot be totally accurate because it's a little bit hard to read the chart. But it's an approximate analysis. This is for preliminary design. And so it's okay. Now there are more charts in the textbook, in Shigley's Mechanical Engineering Design, Chapter 5, any edition. And so, and there are a lot of charts. And why there are a lot of charts? Because you have to look for a chart that has the geometry that you want. For example, in this case, I have an edge crack on a rectangular plate, but could be an interior crack. The plate may not be rectangular. Maybe there is a hole that has a crack. And so there are all kinds of geometries. So for each geometry, there's going to be a different chart. And for each geometry, not only one different chart, but there will be 3 charts because the loading could be axial load, all right? It could be bending, moment, or it could be torsion, which will produce shear stress, torsion T. So there are 3 types of loading for each geometry, and there are many geometries. And if the particular case that you want to analyze or design, it is not in Shigley's, there are handbooks with many more charts. So you can always find what you need, okay? Almost always. Okay, so then now we can do the design. Now for fracture, we got to use the nominal area because remember, you got to forget about the crack in order to calculate the far field stress, right? So in the formula, the far field stress sigma is calculated out there, right? Far from the crack. So basically you calculate with the formulas that you used before in this class, mechanics of material formula that have no crack. So you assume, oh, the crack is not there, I'm going to calculate the stress. Since the stress is calculated that way with nominal area, then the chart was built with that assumption in mind, okay? Right, so we have to use now a nominal area, right? So nominal area is thickness multiplied by B. So this is B multiplied by thickness, that's a cross section. Cross section is 1200, okay? Which is different than what we did for yield. So at fracture, the failure criteria says that when Ki reaches KIC, boom, the crack is going to propagate, all right? So what I do is I rewrite this equation this way, which is the same, just swap these 2 terms. And now I expand, what is this K sub I? K sub I is beta sigma square root of pi a, okay? And sigma is the far field stress, which is P over A nominal. So A nominal, I know what it is because I calculated, but P I don't know because that's what I'm trying to find. So I put P divided by A nominal, all right? Okay, so now we are ready to put numbers, but before we do that, I put this here because I watch the units. You can do whatever you want with these units, the megapascals and the P and the millimeters, all right? But, and it's easy to make conversions, but whatever is on the square root, it has to be meters because the material property was given as 80 megapascals square root of meter, all right? And trying to do a conversion on this 80, taking into account that the meter is inside a square root, is not easy. It's possible, but it's going to confuse you. So the best is just keep anything that is on the square root as meter. So since on this side, the fracture toughness was defined this way, on this side, I'm going to put meters here, even though I'm putting 1200 millimeters there. These 1200 millimeters I put because megapascals is newtons per millimeter square. So I put P in newtons, 1200 millimeters square, and so this is going to cancel with this, and everything's great. But whatever is inside the square root, I just keep it in meters, okay? So we got everything. Now we got all the numbers there. So we can get P. P then is 1200 multiplied by 80 here. 1.3 goes down. This goes down. Okay, and I do this calculation, I get this number, which is ugly because it says 329,000. So we don't like that. We're just going to write 329 kilonewton. Okay, so that will be the load that will take to propagate this crack, 329. Okay, so now since 329 to propagate the crack is less than 958, which will be the load to fail this plate by yield, the load of failure is, you tell me, okay? You tell me, right? Okay, so then we go to another example, all right? So in this example, I'm going to introduce allowable stress design, ASD, okay? Because it makes it easier to do the example and also because you need to know about it, all right? So this is a design example, it's not an analysis. They say, okay, the plate is made of titanium 6Al4V, which that means 6% aluminum, 4 vanadium, the rest is titanium. This is the most common titanium alloy that is used for everything. And okay, for that titanium alloy, we can get the properties from a table that I showed in a previous video. S sub Y is 1035. And KIC is 55, okay? Now we put an applied load of 4 meganewtons, so we know where the load is, and that will produce far field stress, which is calculated this way. And the crack length is 2.7 millimeters. That's a small crack. That's more. This problem is more real than the previous one, okay? A crack of 2.7 in a plate that it is 1.4 meter. Okay, I put meters here to confuse you because some things are in millimeters, some things are in meters. But this is easy. That would be 1400 millimeters, okay? And so we got all these things, and they say, oh, please tell us what the thickness should be to get a safety factor 1.3. Right? This is more challenging problem, more interesting, all right? So then we go to the next slide, and guess what? First, we do design for yield. Even though I'm in fracture mechanics, we always have to check yields first, all right? So, okay, but in order to do this, I'm going to introduce the allowable stress. I mentioned this before in another video, that when you have a safety factor, you can do two things. You can put the safety factor on the load and magnify the load, and then you do the analysis. Or you can put it on the strength, and you reduce the strength, and you do the analysis with the actual load, okay? So which one you do? Well, it depends on convenience. Whatever it makes your life easier. In this example, it makes my life easier if I put the safety factor on the strength. So basically I'm saying, okay, the material has an S sub Y, which is 1035 megapascal, that's the yield strength. But since I want a safety factor of 1.3, I'm going to reduce this number, and I'm going to pretend that my material can take only 796. When I pretend that the material takes 796, I'm introducing already the safety factor into the strength. And from then on, I don't have to worry about the safety factor because it's already there in this number. And this number is called allowable stress. That means how much stress they let me allow use from the actual strength, which is 1035. That's easy, right? Simple concept. All right, so then we, armed with this knowledge, we proceed. Of course, for yield, we gotta use net area. Remember from the previous example, the only area that remains is this, so I'm gonna use that. All right, but I don't know the thickness, so I cannot calculate yet. Okay, so in allowable stress design, the design is acceptable if the stress is less than the allowable. If you exceed the allowable, then the safety factor is not going to be 1.3. If it is equal, sigma equal to sigma allowable, the calculated sigma equal to sigma allowable, then the safety factor will be exactly 1.3, okay, and that's the limit. So I put this equal there, yes, for 1.3. And sigma, how is calculated? P divided by the net area, T, B minus A, okay? So I got P divided by B minus A, sigma allowable, move it here, move the T up there. And so I put the numbers, B 1400 minus 2.7. So you see, it's going to be almost 1400, yes? As a matter of fact, in the textbook, this example is done. They put directly the 1400, but then it makes it confusing because the students think that we're using the nominal area. No, we're not. We're using the net, okay? It's just that the crack is small, so it takes a little bit of it. But in example 1, the crack was big, and this made a difference. So I use it always. I don't care how small it is. I will subtract 1400 minus 2.7. Multiply by the sigma allowable, which I already calculated, is there, 796. And this is the load that is given. I put this, and it says, oh, the plate has to be 3.6 millimeters. Otherwise, it's going to yield. All right? So that will be the design for yield, accounting for yield. But this is a crack, and so this design is not good. We have to do more than this. So we go to the next page. Now we design for fracture. Okay, to design for fracture, then what do we do? Okay, we start with safety factor. So the safety factor in fracture mechanics is the ratio of fracture toughness divided by stress intensity. Like I told you in one of the previous videos, on the top of the, to calculate safety factor, on the top you put what you pay for, that's the material that you buy. It has a KIC value. And on the bottom, you put something that it is the solicitation. That means, you know, how much stress intensity you want to put. Okay, you notice that I'm not saying how much stress. How much stress intensity you want to put. Because it's a combination of the stress and the length of the crack, all right? And you remember Mr. Griffith, he said that the product of the stress times the square root of length of crack is a constant. So stress intensity multiplied by pi here inside because Irwin likes it to put the pi. So stress intensity goes with this formula, which by now you should know by heart, okay? Beta sigma pi A. Okay, so I put it inside here and I get eta, okay, I see divided by all this stuff, all right? Okay, so now we know eta, yes, and we can calculate sigma allowable. Now, why I put this sigma allowable there? Because this eta is fixed, 1.3, all right? So when this equation will work for any sigma, but if you know the eta, 1.3, then this becomes the sigma allowable, which will be how much stress you can put, far field stress. So we can calculate the sigma allowable as KIC over beta eta pi A, all right? Now, it's important to notice here that this sigma allowable is not a material property, okay? And it's not just proportional to a material property. It's a value of far field stress for this particular example. So please don't calculate this number and then use it for another example because it's not going to work, all right? Because sigma allowable is a function of A and beta. And you know, A and beta, they change all the time. So it is not a material property and it's not proportional to a material property. All right, it's just one number that we calculate for this particular example to make the solution easy, okay? So, okay, so then, all right, we got this equation for sigma allowable, but it has beta, so we gotta get the beta. Okay, to get the beta, we enter H over B, 1400 over 1400, because H and B are both the same. And so that's 1, so that we go in this curve again. And then A over B is 2.7 over 1400, which is approximately 0. So that means that we are here on the axis. And okay, so then from the chart, you see the chart starts not at 1, it starts a little bit above, so I put 1.1. And once we have the beta, we can calculate sigma allowable. Again, I put this for this example only. For every example, every variation, you got to calculate the sigma allowable again, okay? This I'm saying because if you are used to do ASD, allowable stress design, then if you do a strength design, the sigma allowable is fixed, because once they say, oh, the safety factor gotta be 1.3, then you knock off the real yield strength by 1.3, and this number it never changes. But in the context of fracture mechanics, this number is changing all the time, okay? It's just that I use it for convenience. So sigma allowable is what? KIC from the table, we know is 55. Beta is the number I got right here, is 1.1. This 1.3 is the safety factor, 1.3. And this is the length of the crack, which you see again, I put in meters, all right? Because this number 55 is a square root of meter, so I need a square root of meter on the denominator to cancel them out. And then the megapascal will come over here, 418. That's the sigma allowable for this example. Now, the nice thing about the sigma allowable is that then now I can say the thickness is P over V sigma allowable, right? Because sigma is P over TB, nominal. And so I can come up with this formula. And so I put 4 meganewtons. B is 1400 and 418. Okay. And why 1400 and not 1400 minus 2.7? Because when we do fracture, we use nominal. Okay. Like if the crack is not there. And I get 6.8 millimeters. All right. Okay, so for fracture, for this crack to propagate, not to propagate, to avoid it to propagate, the plate has to be at least 6.8 millimeter thick. Okay, so anything less than this, the crack will propagate, right? More, it won't. And so now 6.8 millimeter, which will be the thickness, minimum thickness that you need to not propagate the crack, is larger than what we calculated to avoid yield, which was 3.6, all right? So the design calls for T, what are you gonna tell the guys in the shop to make, a 6.8 millimeter plate or a 3.6 millimeter plate? You tell me, okay? You have to tell me. You can tell me in the comments and I'll tell you if you got it right or wrong, okay? So great, with that, I think we got the fracture mechanics covered. The videos, okay, are posted on the forum for the registered students and then eventually on YouTube. And that's what I would like the questions. If you have questions, registered students make it on the forum and everybody else on YouTube. And I will try to answer the questions the best I can. Okay, and so that's pretty much it. So now I got to gear up and work on the videos for fatigue, okay? And remember, on fatigue, we're gonna use the knowledge that we have gained from the lectures on stress concentration and fracture mechanics. Both, all the things, phenomenological, all the explanations of the first video of fracture mechanics and stress concentration play a role in fatigue. So you have to see these videos, otherwise my explanation is going to be very hard, very difficult to understand, all right? So with that, I thank you very much and see you soon.